Today we're going to be answering an FRQ from 2005, question number 6. So here we are given a differential equation dy dx is equal to negative 2x all over y. And for the first problem, we're supposed to sketch the slope field for the given differential equation, and the points are provided to us. And it's going to be from x negative 1 to positive 1, and for the y values, it's going to be from positive 2 to negative 2. Which is something similar to this one. So to sketch the slope fields, we're going to start by writing out our differential equation, which is negative 2x all over y. So to organize our slope fields, I'm going to start working on the slope of the first column. So on the first column, the x's will be consistently at negative 1. And the y is going to start at 2 up until negative 2. So we have 2, 1, 0, negative 1, and negative 2. So let's add another negative 1 right here. And let's solve for the slope for each coordinate. So to find the slope, we need to use the formula negative 2x all over y, which is our differential equation. So if we're going to find the slope of the first coordinate, we'll have negative 2 times negative 1 all over 2, which is going to give us positive 2 all over 2, or simply 1. So that is going to be our first slope. And to move on to the next slope right here at coordinate negative 1, 1. So by inspection, 2 times negative 1 is positive 1 all over 2. So we'll have, or 2 times negative 1 is positive 2 all over 2. So this is going to be 2. Positive 2 all over 1. And for the third coordinate, we have negative 2 times negative 1 all over 0. So this one is undefined because the denominator is 0. And for the third one, negative 2 times negative 1 is positive 2 all over negative 1. So this is negative 2. And this one will be at negative 1. So that is the slope field for our first column. And if we're going to sketch it in our xy plane, so we have 1 and 2. So we know that 1 is closer to a horizontal line, which is at slope that's equal to 0. So this one is less steep than 2. So I can sketch this as such. So that's the slope field, which is a positive slope, which is a little bit closer to a horizontal line, because if we're going to represent a slope of 2, it's going to be steeper than the first one. So we can graph our slope like so. And since at x equals negative 1, y is 0, so it's undefined using our differential equation, so we don't need to graph it. For y equals negative 1, we have negative 2, so we'll have a steeper slope that is negative compared to negative 1. So we'll have this slope right here, and for negative 1, we'll have a slope like so. So that is the sketch of our first column. And to sketch the second column, at y equals 0, so in this case, at y equal to 0, so if these are, or at x equal to 0, we know that our numerator will just turn into 0. So that means all the slope for our second column will just be a horizontal slope, because the slope is going to be equal to 0. So if you want to see it, it's just going to look something like this. So let's say negative 1 and 2. So m is equal to negative. So 2 times negative, this is supposed to be 0. 2 times 0 all over 2 is just going to be 0. So the slope is going to be 0. And it's going to be consistently 0 even though y is changing, because the numerator will just turn into 0. So for the second column, this one is easy to represent because all of them are just horizontal lines. So we have horizontal line right here. However, when x is 0 and y is 0, m is undefined. So we don't need to represent an undefined slope right here. Or you can also use a vertical line for the representation of an undefined slope. And for the rest of the coordinate, we will still have a horizontal line because it's still going to have a 0 numerator. Now for the third column, so the third column we have x, y, and m. Now we have positive 1, and we start at positive 2 up until negative 2. So just to illustrate the first slope, we have m equals negative 2 x all over y. So if negative 2 times 1 all over 2, it will give us negative 1. So the slope for our first coordinate for the third column will be negative 1. And if you will notice, it will just behave the same way as my first set right here. The only difference is that the first two coordinate at positive y will be negative, and when y is negative, in this case right here, the slope will be positive. So this one will give us negative 2 because negative 2 times 1 is negative, all over positive 1 is still negative 2. And this one is still undefined because the denominator will still be 0. And if it's y equals 1, negative 2 times positive 1 is negative 2 all over positive 1 or negative 1. So this is positive or positive 2, and this one is going to be positive 1. So these are the slope of our third column, and to illustrate this, now we have a negative slope which is closer to 0, so this one is less steep than negative 2, so negative 2 or negative 1 can be represented as such, and for negative 2, which is steeper than negative 1, so we'll have this graph right here, undefined at y equals 0, and for this coordinate we have positive 2, so this one is steeper than the other one that we're going to be constructing, so this one is 2, and the other one, which is at negative 1 or positive 1, so it's increasing and it's closer to a horizontal line. So that is how we represent the slope field for problem letter A. And to answer problem letter B, in problem letter B, we're supposed to find the particular solution of the differential equation with an initial condition of f of 1 is equal to negative 1. So for letter B, f of 1 is equal to negative 1, which means the coordinate will be at 1 and negative 1. And we're supposed to find the tangent or the line tangent to the graph at 1, negative 1. And we are going to use this equation to approximate f of 1.1. So since we are given the point, we're just supposed to find the equation of the tangent line. So to use the point slope form, y minus y sub 1 equals m times x minus x sub 1, we'll be able to find our tangent line at point 1, negative 1. So we have y plus 1 equals m of x minus 1. And to find m, all we need to do is to find the slope of the function, which is given in our differential equation dy dx, which is at negative 2x all over y. So plugging in the point 1, negative 1, so we have negative 2 times positive 1 all over negative 1, which is going to give us positive 2. So the slope of this tangent line is at 2, so we have y plus 1 equals 2 times x minus 1. So by simplifying this, we'll be able to find the approximated value of f of 1.1 by having y, or isolating y. We'll have y plus 1 equals 2x minus 2, y equals 2x minus 2 minus 1, so y equals 2x minus 3. So this is our tangent line, and to approximate the value of f of 1.1, we just need to replace x by 1.1, and 2 times 1.1 is 2.2. Subtract it to 3, and we'll have the approximated value of f of 1.1, which is equal to 0.8 or 0.8. So this is how we answer problem letter B. And to answer problem letter C, now to solve for letter D, we need to find the particular solution of y equals f of x, given the initial condition of f of 1 is equal to -1. So our differential equation is equal to negative 2x all over y. And we need to find the particular solution at f of 1 equals -1, therefore x is equal to 1 and y is -1. So by separating our function, we'll be able to integrate this function so we can find our y equals f of x. So by cross multiplication, we can have y times dy equals negative 2x times dx. So now that we have separate our function, we can now integrate each function right here, and we know that the integral of y dy is y squared all over 2, and the integral of negative 2x dx is negative 2x squared all over 2 plus c. So by simplifying this, we'll have y squared all over 2 equals negative x squared plus c. And to have y by itself, we can multiply both sides by 2, leaving us with y squared equals negative 2x squared plus 2c. So we know that we can change our constant 2 times c into another variable, so we can have y squared equals negative 2x squared plus d as the rule on evaluating integral or separable equation. So now from here we can solve for the constant d by substituting the value of x and y to our general equation. So this is now our general solution. For the differential equation, all we need to do is to find the constant d. So y squared is negative 1 squared equals negative 2 times 1 squared plus d, giving us 1 equals negative 2 plus d. So we have 1 plus 2 equals d. Therefore, d is equal to 3. So d is equal to 3, and since we have our constant right here, we can now plug it into our general solution. So y squared is equal to negative 2x squared plus 3. And if we want to have y by itself, we can get rid of the exponent and write our equation as negative 2x squared plus 3. So this is now our particular solution. At 1, negative 1.